Hello everyone and welcome back. My name is Mr. Kowalt, and in this video I'm going to be going over creating a buffer and finding its pH. So let's get into this. Okay, so in my last video we talked about what a buffer was and what the two methods are of making a buffer, right? So you could either just throw amounts of an acid, a weak acid, and its conjugate base, and just throw it in and mix it in and you've got your buffer. Or another way you could do it is by starting with just the weak acid and then reacting it with a strong base, a partial amount, right? So you add some amount of the strong base, it's going to react with the weak acid, creating leftover weak acid with its conjugate base, and you've got the buffer, right? So here I'm going to go over an example problem of how to create the buffer, right, mathematically, and then to figure out the pH of that buffer. Okay, so let's get started. So in this first example, we're told to start with 0.040 moles of the weak acid, no conjugate base, and then we're going to add 0.022 moles of strong base in 100 milliliters of the solution. So we're going to make 100 milliliters of the buffer solution, and we're going to do it by taking 0.40 moles of the weak acid and reacting it with a strong base, 0.022 moles. So the first thing we want to do is start with what is called an IF table, or what I call an ICF table. It's like an ICE table, but remember this is used for when reactions go to completion, when they're 100% like reactive, like in this case. Anytime you react a weak base with a strong acid, or anytime you're reacting strong acids or strong bases together with something else, it's going to go to completion. And so you want to do a kind of a stoichiometry problem first, right, in terms of moles, and then figure out what you end up with at the end of that reaction, and then from there go on to do the equilibrium problem like you normally do, and we'll figure out the pH doing an ICE table. So again, first thing you want to do is have everything in moles. If they don't give you something in moles, then you got to convert it to moles first before you do the stoichiometry. And then when you do the ICE table, then you got to convert back to molarity to do the ICE table. Don't do your ICE table in moles. Okay, so unless, of course, you've got 1 liter of the substance, and then moles and molarity should be the same. Okay, so let's get into this. So you set up your ICF table or your IF table, and you have everything in moles. Notice that I have things in millimoles, and that's the only reason for that is because it makes the calculations easier. The numbers are easier to work with. You don't have to have decimal points. Here you have 0.040 moles. Change that to millimoles, and you got 40 millimoles. So 40 seems like an easier number to work with than 0.040. So same thing with 0.022. Instead of that, we have 22 millimoles. So initially we start with 40 millimoles of the weak acid, 22 millimoles of the strong base. This is going to react completely, and we have 0 water produced. I mean, we're doing this in water, but we haven't produced any extra water molecules yet, so that's 0. And then we have 0 of the nitrate, the conjugate base. Okay, so what we do is we just do a stoichiometry calculation. So the hydroxide ion is going to completely react with the weak acid. It's a 1-to-1 ratio, so when we react to this, all of this is going to be gone. So we're going to lose 22 millimoles of the strong base, and therefore it's going to react with 22 millimoles of the acid, so we're going to lose 22 millimoles of the weak acid, and that means we're going to create 22 millimoles of the water, and then we're going to create 22 millimoles of the conjugate base. Now the water we don't really care about because it's liquid. This is happening in water, so we're really not going to be interested in this so much. And it's not really going to affect the volume, so we don't have to worry about that. We're really going to be interested in the base, the weak acid and its conjugate base. So this is going to go to 0. We're not going to have any of the strong base left over. We're going to lose 22 here, so we end up with 18 millimoles of the weak acid, and then we end up, of course, with 22 millimoles of the weak base. So now at the end of this reaction, we have some acid, weak acid, and its conjugate base. We now have a buffer system going on here. So now we could do our ice table. Okay, so before we go to the ice table, let me talk about the equilibrium constant for this reaction. If you pay attention, right here they give us a weak acid reacting with a strong base, and that gives us water and NO2 minus, the conjugate base. Now, to figure out the K value, if you pay attention to what they give you, you might recognize that this reaction is the reverse of the base, the conjugate base reacting with water, right? So if you remember, your KB value, the equilibrium constant, dissociation constant for a base, a weak base in water, is your KB. That's your KB, right? So basically we have the reaction with your weak base with water producing OH minus and the conjugate base, or the conjugate acid, right? So it's been reversed. So we're going this way, but the reaction this way is the reaction of a weak base with water, and that's your KB value, which means that the K for this reaction is equal to the inverse of that, because we flipped it, right? So because we flipped it, right, so we have K of this reaction is going to be 1 over KB, the inverse of the KB of the opposite reaction here, right? Okay, so then if we also remember that KW is equal to the dissociation constant for an acid, your Ka, multiplied by the dissociation constant of the conjugate base, the Kb, right? So these are related to each other by the inverse of the Kb, or your Ka value or your Kb value. So these are related by the weak acid and its conjugate base, right? So these are both the Ka values and Kb values of those related conjugate acid-base pair. And so Kw is equal to the Ka times the Kb, right? And we could use that to solve for Kb for NO2, right? So you can't look up the conjugate, excuse me, you can't look up the conjugate base Kb value or the conjugate acid Ka value. Well, you can look up the acids on a table, but your Kb values for conjugates are not going to be in there. You don't look up conjugates, you look up the weak acid or the weak base. The conjugate you have to look up by this equation here. So you got to use this to find the conjugate. You're not going to find the conjugate in a table. So you find the Kb value for NO2 minus by taking Kw dividing by the Ka for the acid, which you can look up on a table, and then put it all together, and you get the K value for this reaction is equal to 1 over the Kw divided by Ka, right? So this then becomes the calculation. So just wanted to kind of go over that as a review in case you needed a review. That's it. Okay, excellent. So let's move on. So now we can do our ice table. So I'll put up the ice table, but before we do, there's 2 ways that we can write the equilibrium expression, and we'll go over both of those and calculate the pH in those 2 ways, and we should get the same answer. So stay tuned. I'll be right back. Okay, so we're back. So first, I forgot to mention that when I was talking about the Ka value over here, like how to calculate the Ka value, I'm sorry, the K value for that reaction, I forgot to actually give you the K value. So you can see here the K value for for that reaction was 1.4 times 10 to the 9. You can see that this is a very large number, and therefore that indicates that that reaction would go to completion, which is the whole point that we did the ICF or the IF table first. We did the stoichiometry first because the K value indicates that that baby is going 100%, right? So it's going to go all the way. So you do the stoichiometry first, and then you do the ICE table with the equilibrium. So next thing, when you're setting up your equation, what we had left over, we had some weak acid left over, we had the conjugate base left over, and we had water. We had those three species left over. And so we have to write an equilibrium equation using those three species. Now, the conjugate acid, the weak acid and its conjugate base, or the conjugate base and its weak acid, they're not going to react with each other. So they're going to be on opposite sides. So again, there's two ways you could set up this equation. This is one of them, where I have the weak acid reacting with water to produce the hydronium ion, H3O plus NO2 minus. And you'll see here that we start with the 18 millimoles of the acid. Oops, excuse me. Sorry about that. Okay. So we have the 18 millimoles of the weak acid. We have the 22 millimoles of the weak conjugate base left over, just like we saw at the end of the previous part. And you'll notice here that I'm dividing by 100 milliliters, right? So remember, we made 100 milliliters of this stuff. We want to convert back to molarity. We want to go back to concentrations, because that's how you do your equilibrium, because it's based on concentrations. And so we got to have concentrations when we're working with the ICE table. And the great thing about having it in millimoles is that you don't need to convert to liters to find the concentration in molarity. So if you have millimoles, then you can just keep your volume in milliliters, which is usually what the volume unit is, and you can just do it right off there. So, so the millimoles is going to cancel out with the milliliters, okay? Or I shouldn't say cancel out, but the milli is going to cancel out. Let me redo that. So we have millimoles and milliliters. So the milli is going to cancel out, and you got moles per liter, and you get your molarity. So same thing here, 22 millimoles. Milli cancels out with milli, so moles over liters, and you get your concentration. Okay, so now that we have that, so we have 0 H3O plus, so that means that it's going to go this way, because you can't have 0 of something at equilibrium. So it's going to go this way. So we know it's going to shift this way. Again, water is a liquid. It's in water. That the concentration of water is not going to change. So we don't care much about water. It's not even in the, because it's a liquid, it's not in the equilibrium constant expression. So we'll deal with that. Sorry, bell rung. Okay, so we're going to lose an X amount. So for the change, we're going to lose an X amount here, and it's all 1-to-1 ratio, so it's 1X here. We're going to lose a 1X here. We're going to gain an X amount here, and we're going to gain an X amount here. So that means we're going to have 18 minus X here. We're going to have X for the final amount, and here we're going to have 22 minus, plus X here. So now we have our equilibrium concentration expressions in terms of X. Now we can plug this into our K expression for this reaction. So if we write our equilibrium expression for this acid, so Ka, since this is the weak acid reacting with water, that's your Ka value. So that gives you Ka value. So that's going to be equal to products over reactants. So it's going to be the H3O plus concentration multiplied by the NO2 minus concentration divided by the concentration of NO2. Again, we're not including water because water is a liquid and liquids and solids do not end up in the equilibrium constant expression. Okay, now we just plug everything in. So we have X for our hydronium, so that's going to be X. We have 22 plus X for the NO2 minus concentration at equilibrium. So that's going to be 22 plus X. If I said minus X, I meant plus X. And then on the bottom we have our HNO2 concentration. Oh, I said minus because of that minus. Anyway, so we have 18 minus X. So we have 18 minus X. And so now we have our setup. So here we can start to do this. So the Ka value, you can look that up in a table because it's in a table. So that's going to be equal to 7.2 times 10 to the negative 4. 7.2 times 10 to the negative 4. So this is a fairly small number compared to the concentrations we are working with. We have 22 and 18, right? So, oops, I forgot to divide by the 100. So if I divide this by 100, oops, so 18 divided by 100, 22 divided by 100. So 22 divided by 100 is going to be 0.22, and 18 divided by 100 is going to be 0.18. Sorry about that. So the concentrations here are like -1, right? 10 to the negative 1 concentrations. And here we have 10 to the negative 4. That's a difference of about 1,000. So we can be confident that our X is small approximation will work. So let's go ahead and do that. And then we can check it with the 5% rule if we want to. So then we can get rid of this X, we can get rid of that X. And so therefore, 7.2 times 10 to the negative 4 is going to be equal to X times 0.22 molar divided by 0.18 molar. And then we can solve for X, right? Then we solve for X by multiplying 0.18 times this side, 0.18, right? So that cancels out. Then we divide by 0.22 molar. Then we divide this side by 0.22 molar. So then that cancels out. And then we have X equal to this. And then we get, what do we get? 5.89. So then X is equal to 5.89 times 10 to the negative 4. And so X, you can see, again, that's our hydronium concentration. Remember, pH, which is what we're trying to find, like, so find the pH, right? So we know that the pH is equal to the negative log of the H plus concentration or hydronium ion concentration, which is right here, X. So X, we just found our H plus concentration, so we plug that into this equation, right? So pH is equal to the negative log of 5.89 times 10 to the negative 4, and we get 3.230. pH is equal to 3.230. And just as far as sig figs go, so for significant figures, notice here that we have 2 sig figs there, 2 sig figs there, right? That's 4 sig figs, right? So when we divide here, we end up with 2 sig figs again, right? So when we're multiplying and dividing, we have 2 sig figs here. So we have 2 sig figs here. So basically our answer should have 2 sig figs. We're keeping an extra sig fig here just to make sure that we're avoiding a rounding error. The thing about sig figs and the logs is, and here's the rule to follow, notice that the number of sig figs here that I have are 2. I'm keeping an extra digit, right? So whenever you take the log of a measurement, whether it's negative log, positive log, whatever, if you take a log, and this also works for like the natural log. So anytime you take a log, base 10 or natural log, the number of sig figs or digits you have here will translate into decimal places here. So notice I have 3 digits here. So that means that when I take the log of this number, that value I get should have 3 decimal places. So if you look over here, I have 3 decimal places. But notice that this 9 here, that 9 is not significant. I just kept that. So that means that the 3 here is the last sig fig. So if I'm looking just at these 2 numbers, these are my 2 sig figs. So that means that I should cut it off at 2 decimal places, but I kept an extra sig fig, so I kept an extra decimal place. So this 0 is not significant, it's just, I'm keeping an extra one just in case, right? So technically it would be 3.23 would be the answer to this problem. Now, let's try the other way. So there's another way you could set this up, and that would be where you switch these around. There's no reason why you can't have the conjugate base on this side and the weak acid on this side and just flip the problem. So let's go ahead and try that. Okay, so here's the second way of solving this problem. I can take the other reaction, I can reverse it. So in this case, instead of before I had the weak acid reacting with the water to form the conjugate base, but now I have here the conjugate base reacting with water to form the conjugate acid. And so in this case here, we set up our ice table again, but this time since we're showing the conjugate base reacting with water, we're going to need the Kb value. And the Kb value, remember, for a conjugate base is not going to be in a table. You're not going to be able to look it up, so you need to calculate it using the Ka value for the weak acid that you can look up, right? So here we have Kw is equal to Ka times Kb. Solve it for Kb for the conjugate base, right? And then it's the Kw divided by the Ka of the weak acid. So the Kw is 1.0 times 10 to the negative 14. We saw that the Ka value for our weak acid was 7.2 times 10 to the negative 4. Divide them and you should get 1.38 times 10 to the negative 11. Right? Notice we have 2 sig figs here. My answer has 3 sig figs. I'm keeping an extra sig fig for avoiding rounding mistakes. So here's our Kb value that we're going to use. Now here's the ice table using our new equation. So we have the conjugate base reacting with water to form hydroxide ion and the weak acid. So now we have the 22 millimoles on this side divided by 100 milliliters. And then we have 18 millimoles divided by 100 milliliters. Remember, the milli is going to cancel out. So we have moles per liter, and then we have milli cancel out. And so that's going to give us 0.22 molar and 0.18 molar. Okay, so again, since we start with 0 amount of the hydroxide in solution, so that means that it's going to go this way. We're going to shift this way, and we're going to make some hydroxide ion. So then we're going to lose again an X amount on this side. And again, it's all 1 to 1. So we got 1x minus 1x here. We're going to have a plus X amount and plus X amount there. And then we end up having, again, if we divide this, it'll end up being 0.22 molar minus X. This is just going to be your plus X. And this is going to be your 0.18 molar plus X. Okay, now we can set up our equilibrium constant expression. So remember your Kb in this place is going to be products over reactants. So we have the concentration of OH minus times the concentration of HNO2 divided by the concentration of NO2 minus. And again, that's going to be equal to this value here. So we plug in everything. We plug in our equilibrium concentration in terms of X. So OH minus is going to be X. So we have X multiplied by the HNO2 concentration, which is this 0.18 plus X divided by the concentration of NO2 minus, which is 0.22, 22 minus X, and that's going to be equal to the 1.38 times 10 to the negative 11. And you can see right away that this is a really, really small number, so that means that X is going to be really, really small, so we can ignore it. And again, you can check with the 5% rule if you want. So we're going to get rid of that X, we're going to get rid of that X, and then we end up with X times 0.18 divided by 0.22 equal to 1.38 times 10 to the negative 11. And then we just solve for X, right? So we're going to multiply both sides by 0.22, 0.22. So that cancels out. Notice the molarity. I'm not writing the molarity because that cancels out anyway. So it's going to be, you don't need to write it. And then we're going to divide by 0.18. So that's going to cancel out here. And we divide over here by 0.18. And then when you calculate this out, you get the same answer you did before. It was 3.23, 3.230. Right? And again, remember this is actually 2 sig figs. This is 2 sig figs, this is 2 sig figs. The least number of sig figs is 2, so your answer should be limited to 2 sig figs. So we have that there. We keep it extra in this case, right? So we've got this, and then we do the pH again, right? So if you do the pH again, remember it's the same answer, so the pH is going to be the same. So pH is equal to the negative log of, oops, no, I'm sorry, that's not the pH, that's not the number, that's the number we got is 1.69 times 10. That's 1.69 times 10 to the negative 11. There, that's much better. Sorry about that. So that's the answer we get. Then we take that and we do the negative value. And so again, we have 2 sig figs here, but we're keeping an extra digit to avoid rounding. So when we do the pH is equal to the negative log, we get 1.69 times 10 to the negative 11. We take the pH of that. Oh, by the way, just so you know, it's not pH. What am I doing here? This would be pOH, right? Because you got to pay attention to the fact that we're looking for the OH minus concentration. So what we found here was X. So X, this is equal to X. But what is X? X is your hydroxide ion concentration. So students make this mistake all the time where you forget what you're solving for and you assume, oh, I got my H plus concentration. But here we have the OH minus concentration. So, but it's asking for pH. Remember, pH is the negative log of the H plus concentration, but we have OH minus, the hydroxide ion concentration. So you could still do the negative log, but it's going to be POH, not pH. So if we do the POH, I almost made that mistake. So the POH, let me calculate this. 10.7, what was that? 10.770. I keep an extra digit here, and then what you do is to get the pH. That's going to be equal to the pKW, which is 14, minus the pOH. So then pH is equal to 14 minus 10.770, and then you get the pH is equal to the 3, oops, let me look again, 3.230, 3.230, and you get the same pH again. So it doesn't matter whether you do the acid, weak acid reaction with water, or if you set up your ice table with the conjugate base reacting with water. So either one will get you to the right pH. So I just wanted to show that, so that way you're not confused, or so just the thing is, when you ever have a buffer, you're going to have the conjugate base and the weak acid. They're not going to react with each other, and you have water. So you set it up so that one of the species, either the weak acid or the conjugate base, or the weak base or the conjugate acid, depending on the reaction, is going to react with water to produce the other conjugate, and whatever other species makes sense. Okay, so that's it for this video. I hope you enjoyed this example problem. In the next video, I'll do another example problem and show you all of this again using a different problem. So if you enjoyed this video, please like, share the video, hit that like button somewhere around here. My arm, I don't know, it's somewhere over here. So like, share, subscribe to the channel, hit that notification bell up there somewhere, so that way you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me. Have a great day.